This is Lecture 2 from Module 7 in the book Problem Solving Guide for Mechanics and Thermodynamics, Statics with Trigonometry. You should have a fundamental understanding of torque by now. So problems in which the force and distance are not at right angles should not be too much of a challenge. So let's consider a 20 kilogram ladder placed against a vertical wall. The ladder makes an angle of 77 degrees with the horizontal. We're going to assume the wall is frictionless and the ladder is uniform. So the center of mass is in the middle. What is the horizontal force with which the wall pushes on the ladder? There's no frictional force here, so the wall can only push out horizontally. So let's start with the force diagram. You should have a lot of practice with force diagrams. We have gravity in the middle of the ladder. We have the normal force from the ground. I put a subscript G here for the ground. We have the frictional force from the ground, and we have the normal force from the wall. The wall's pushing on the ladder to the left. The ground's pushing up on the ladder. There's a frictional force, or else the ladder would just slide, and there's the gravitational force. We know the gravitational force is 200 newtons. It's mg. M is 20 kilograms. G is 10 newtons per kilogram. To get the normal force from the wall, we can take torques about the base of the ladder. And let's mark that spot with the red dot. We're taking torques about this point. This eliminates the normal force from the ground and the frictional force. Gravitational force is L/2 away from this point, halfway up the ladder. And the normal force from the wall is the entire length of the ladder from this red dot, the point at which we're taking torques. So now we need to get the components of the gravitational force and the normal force from the wall that are perpendicular to these distances, because these are the components that rotate the ladder about the point of rotation. The component of gravity that's rotating at about this point is right here. There it is. F gravity cosine 77. That's 77, that's 13, that's 77. F gravity cosine 37 is perpendicular to L/2. That's rotating it clockwise. The force that's rotating it counterclockwise is the normal force from the wall, and we have to make it perpendicular to the ladder. So it's right here. This is 77, that's 13, that's 77, that's 13. So F normal wall, cosine 13 degrees. So let's get rid of all the other forces except for the ones that are rotating the ladder about the point of rotation. There they are. So now we can write the torque equations. L/2, F gravity cosine 77 is the clockwise torque. Torque clockwise, and the torque counterclockwise is the whole length of the ladder times F normal from the wall, cosine 13 degrees. The ladder is not doing anything, it's static, so these torques must be equal. So we set the clockwise torque equal to the counterclockwise torque, and we can solve once we put in 200 newtons for F gravity, and we get 48 newtons. So F normal from the wall, straight out, is 48 newtons. This also means, incidentally, that the frictional force must be 48 newtons this way, because the sum of the forces in the x direction is 0. There's another way to get the answer to this problem, and it's worth going over. Instead of getting the components of the force that are perpendicular to the distances, we can get the component of the distance that's perpendicular to the force. You don't need to do this. You can certainly always get the component of the force that's perpendicular to the distance, but sometimes it's easier to get the component of the distance that's perpendicular to the force. So I'm just going to show you how it works. Let's go to the original force diagram. Those are the four forces. F normal from the ground must be 200 newtons. It has to balance gravity. It's the only thing that's holding the ladder up, and the frictional force must balance the force, normal force from the wall. So now we go 200, 200, 48, 48. Let's get rid of the forces that don't produce torques. Let's get rid of these two. We don't need these on the diagram. We're taking torques about this red dot. Let's get rid of those. That's better. We're going to get the component of the distance that's perpendicular to the force. So we're using the entire force. Previously, we used the entire distance and a component of the force. Here we're using the entire force and a component of the distance. How far is this force? What's the perpendicular distance of F gravity from this point? It's right here. There it is. It's a right angle. So that's the distance the force of gravity is from the point of rotation. The normal force from the wall is this far away. And what are these distances? This is L over 2, cosine 77 degrees. This is L, cosine 13 degrees. So the clockwise torque from gravity, we have the whole gravitational force and a component of the distance, L over 2 cosine 77 degrees. That's this distance right here. The counterclockwise torque from the normal force from the wall, that's L, that's 13 degrees. L cosine 13 degrees times the entire normal force from the wall. These are exactly the same equations we had previously. The only difference was the cosine 77 was with the gravitational force. The cosine 13 was with the force, and we were using the entire distances. Of course, it's the same equation. You're going to get the same answer. All right. When solving statics problems, it's a good idea to invest some time figuring out a point to take torques. It's usually not a good idea to take torques about a point where the force you are trying to determine is acting. So if you wanted to get the normal force from the wall, you shouldn't take torques about this point here. You can if you want. You can get the answer that way. It's going to be a lot more math. But if you take torques about this point, F normal from the wall will not be in the equation. It'll be a lot more math. You can do it. If you love math, then take torques about that point. Of course, you should be investing time getting the force diagram right as well. Now it's time for you to do some problems. Go.